Okay, let's talk a little bit about conservative vector fields. Um, these are vector fields that are very special. They are vector fields that are the gradient of some scalar function. So most vector fields are not conservative, but any vector field that is the result of taking the gradient of a scalar function is conservative. These vector fields interact very nicely with line integrals. And that's the big idea of the day. They kind of do a fundamental theorem of calculus. So um, if your function, if your vector field is of the form gradient of f, then the path that you take from point A to point B in space doesn't matter when you're doing the integral f dot dr. All you have to do is, if you're integrating capital F dot dr along a path, you just take little f minus the of the endpoint minus little f of the starting point and subtract. That should sound familiar because that's exactly what you do in Calc 2 when you find the antiderivative. So in some sense, we see this connection to Calc 2. If f can be written as the gradient of little f is in some sense the antiderivative of big F. And so it makes sense that all we have to do is plug in the endpoints to little f and subtract. Um, the, when an integral uh, is independent of path like that, when it doesn't matter whether I go this way or this way, interesting things start to happen. Really complicated paths no longer matter. I have a path that comprises 3 line segments. Doesn't matter. I'll just start at the beginning and at the end, plug them in and subtract. If I have a path that's closed, in other words, it has the same starting and ending point, and the function is the vector field is conservative, then I'm done. It's just 0 because the starting and ending points are the same. So when I plug in the start, plug in the end, and I subtract, I get nothing. So forces are often like this. Gravity is an example of a conservative force field, and there are lots of other conservative force fields. Let's do a quick flyover of the section. So this starts out with a really interesting geometric construction, and that's one of my favorite things about this subject is it starts to mix geometry and calculus in very interesting ways. And if you're going to start mixing geometry and calculus, you've got to start defining things. So first, let's define a closed curve. A closed curve is simply a space curve that has the same start and end point. It's a simple closed curve, or it's a simple curve if it doesn't cross itself. And then it's a simple closed curve if it looks like this. It's closed and it doesn't cross itself. So they're 2 separate properties. Determining whether a curve is simple and closed, this is really just a matter of plotting the thing or thinking about it in deeply, and I'm not going to dwell on that particular aspect of it. So now that we have a curve, and in particular a closed curve, a closed simple curve partitions, at least in 2 dimensions, it partitions the plane into an interior and an exterior. And that sounds like remarkably obvious, right? Here's this trapezoidal curve. Partitions the plane into the blue part inside the curve and the white part outside the curve. Similarly for this little cloud-shaped object or this hexagon. That turns out to be a remarkably difficult theorem to prove, that a simple closed curve has an inside and an outside area. It wasn't proved until really the early 20th century. It's called the Jordan curve theorem, and it's very important to something that we'll do, I think, in section 4 called Green's theorem. So keep an eye out for that. These are what are called simply connected regions. They're the nice regions. They're well behaved. They don't have any holes in them, as opposed to these, which are not simply connected because they have holes inside of them, or these, which are not simply connected because they're simply not connected. In other words, there's a gap. I can't get from this point in the set to this point in the set without leaving the set. So simply connected regions kind of dispel all of these pathological possibilities. And if you're working on a simply connected region, which, let's face it, 99% of the time, that's all we really care about, you get some really nice properties when it comes to line integrals. And we'll see that not only in this chapter, or in this section, but in the next section. Okay, so that's simply connected. And again, you see how we're defining these really interesting geometric ideas. These are ideas that you probably haven't thought about before. So the fundamental theorem of line integrals goes like this. If capital F is the gradient of little f, then you simply take little f, evaluate it at the endpoints, and subtract, and you've got f dot dr. Remember that this is the work integral. It's also the circulation integral, depending on how you want to interpret it. And we now have this, for conservative vector fields, we now have this lovely, simple way of computing it. The proof is actually relatively simple. We start with the gradient of f dot dr, and we compute the line integral. And what we observe is that the derivative of f of r of t by the chain rule is just the gradient of f of r of t dotted with r prime of t. If you plug that in, what you end up with here is a regular old fundamental theorem of calculus. This is a one-dimensional integral like you did in Calc 2, and you're integrating d dt with respect to dt. All that means is I take what's inside f of r of t, plug in b, plug in a, and subtract. And so secretly, the fundamental theorem of line integrals just relies on the ordinary fundamental theorem of calculus back from Calc 2. So that really helps us if you want to compute, for example, f dot dr over some kind of path. Then your job is to, you have two possibilities. You can either just do it the long way, parameterize everything, do the integration, or you can find a little f that is the gradient, whose gradient is big F. And I'll leave that to you to kind of figure out. But here you're given that little f looks like this. Big F is the gradient of this little f. We plug in the endpoints, we subtract, and we get the result without doing any parameterization. So if it's a conservative field, then the work really is finding this potential, which is a little bit easier often than doing this integral. Okay, let's keep going here. So this is the idea of independence of path, and we say that one of these integrals is independent of path if the value of the integral depends only on the starting point and the ending point, not on how you get from one place to the other. And once you have that definition, path independence of conservative fields follows. If f is a conservative vector field, then f is path independent. That follows directly from the fundamental theorem of line intervals, right? Integrals. If f is conservative, then we know that there's a little f, the gradient of which is big F. And we know that to evaluate f dot dr, which is up here, f dot dr, we only need to plug in the endpoints. Therefore, the path doesn't matter. Therefore, independence of path. Here's a picture of that, right? You've got a starting point and an ending point. You've got three different paths there. If f is a conservative vector field, then this integral over C1 will be the same as the integral over C2, same as the integral over C3. Now, this seems pretty obvious once you kind of absorb the fundamental theorem of line integrals, but it's amazing the kinds of things that can follow from this, and that's stuff that we'll talk about in the coming sections. Okay, the path independence test for conservative fields is more of a theoretical idea. If f is a continuous vector field and its line integrals are independent of path, then f is conservative. Okay, nobody's going to have time to kind of test all the possible paths from one point to another point. So this isn't super useful in determining whether f is conservative, but it is a powerful theoretical tool that people use in other subject areas. And this is the proof, and I'll just let you scan that proof. Showing that a vector field is not conservative, however, this is a useful theorem for that. If we can find two different paths where the integrals disagree, then we know, boom, not conservative. So this is not a useful way of showing that a function is conservative or a vector field is conservative, but it is a useful way of showing that it's not conservative. If we can find two different paths that give different line integrals, not conservative. Okay, let's keep going. So conservative vector fields and potential functions, how do you find this potential function? If you have a vector field, how do you find the potential function? Well, what you do is you assume that your vector field can be written as the gradient of some little f. What that means is that the first coordinate is f sub x and the second coordinate is f sub y. And if there's a third coordinate, that's f sub z, right? The partial, because that's how you compute the gradient. The gradient of f, little f, is f sub x comma f sub y comma f sub z. And if this vector field is equal to the gradient of little f, then we just equate the coefficients, f sub x, f sub y, and if there's a third coordinate, f sub z. Amazingly now, we can use this information to just build the potential function little f. We start with f sub x and we just anti-differentiate with respect to x. Doing so, we get x squared y cubed plus some undetermined function of y. And you might say, hey, Schuler, where's that undetermined function of y coming from? Well, that's secretly the constant of integration. But remember, since we're only integrating with respect to x, the constant of integration might secretly depend on y, and we need to throw that in there to have as complete an answer as possible. Once we have f sub x, this sort of skeleton once we have f, this skeleton of f, we're going to take the derivative of this thing with respect to y and set it equal to what we know f sub y should be. So that's what's happening right here. And we set them equal, and we see part of this goes away, and what's left is h prime of y is equal to cosine of y. And then we can solve for h, which is just the sine of y plus some constant here. And we can put that back in up here for h of y, and we have now found a potential function, at least up to some unknown constant. And you should be comfortable with this because this is exactly the same thing that happens when you're doing integrals in Calc 2. You get this undetermined constant, but when you actually do the integral, you plug in b, you plug in a, you subtract, that undetermined constant goes away, not a problem. Same thing happens here when you're doing line integrals. You plug in the endpoints, you subtract, and that constant goes away. So in many cases, we can just ignore that constant when we're doing definite integrals. Similarly, we can do this finding potential functions in R3, and it's really just another equation that you have to deal with. The only substantive difference, once you set f of x equal to this, f of y equal to f sub y equal to this, f sub z equal to this, when you anti-differentiate this with respect to x, you need to introduce a constant that might depend on two variables instead of just one. All right. And then here's an example of finding a potential function. And then finally, there is a very simple test for whether a vector field is conservative, and it relies on Clairaut's theorem of mixed partial derivatives. If f is this vector field, and we want to know if it's conservative, if it is conservative, P is secretly f sub x, Q is secretly f sub y, and R is secretly f sub z. So if this is f sub x and f sub y, if I differentiate f sub x with respect to y and f sub y with respect to x, I get mixed partials. And Clairaut's theorem from way back in chapter 4 tells us those mixed partials should be equal. And that is the core of a test for conservativeness. We just go around and look at mixed partials. If py is equal to qx, secretly f sub xy is equal to f sub yx, Clairaut's theorem, and f sub zx equals f sub xz, and f sub yz equals f sub zy. You go around the horn, you look at all the possible mixed partials. If they're all equal, three tests, this thing is conservative, more or less. There are some caveats that I'll let you read about, but this test is pretty reliable. And if you only have 2 dimensions, then you only need to worry about py equals qx. But if you have 3 dimensions, then you've got this set of 3 equations. So that's a great test. If these things are equal, once again, 99% probability that it is conservative with some caveats that I'll let you read about. And if any one of these fails, 100% probability that it's not conservative. So when you're faced with a complicated line integral, the first thing you want to do is test it and see if it's conservative. If it's conservative, then you don't care about the path anymore. You don't have to parameterize it. It's a lot less work. What you do is you find that potential function, you plug in the endpoints of the path, subtract, and you walk away. Okay, let's do a few exercises here. Let me bring my notes back into the frame here, if I can. All right, here we go. Finally ready here. Let me give myself some space to work. All right, so in 104, we have a line integral. Ignore this little typo here, this comma and this right square bracket. I've reported it to the textbook authors. We have this function, and now that we know about conservative vector fields and the fundamental theorem of line integrals, before you do any work towards parameterizing C or any of that, check and see if it's conservative. So this is P, this is Q. Look at P sub y. So that's the derivative of this thing with respect to y. All right, so we get the derivative of y e to the xy. That's first times the derivative of the second, plus the second times the derivative of the first. And then the derivative of cosine x with respect to y, remember, is 0. All right, so that's P sub y. Let's look at Q sub x. All right, we take the derivative of this term with respect to x, first times the derivative of the second, plus the second times the derivative of the first. So we get that. And then the derivative of the second term with respect to x is again just 0. And what we see is they agree. They're equal. This is conservative. And so the fundamental theorem of line integrals applies. Okay, well, what do we do next? Now we have to find the potential. So we find little f so that f is equal to the gradient of f. What that means is we're assuming now that this first coordinate is f sub x and this second coordinate is f sub y because it's the gradient of little f. All right, well, if we know that, then let's integrate f sub x, which is y e to the xy plus cosine of x. Let's integrate that with respect to x. So integrating this with respect to x is just e to the xy. Integrating this with respect to x is sine of x. And then what do we have to do? We have to include a possible undetermined constant that depends on y because we anti-differentiated with respect to x. That's f. All right, now take this guy and immediately differentiate with respect to y. X e to the xy, that's 0, and then plus h prime of y. We use h prime to indicate that this is an ordinary derivative, not a partial derivative, because there's only one variable in play at this point. That's fy based on the f that we calculated from fx. Now we complete the circle. Fy should also be equal to this piece here, x e to the xy plus 1 over y squared plus 1, like that. And let me add a little bit more space. Let me try to add a little bit more space. Not helpful. All right. Oh, also not helpful. God, the struggle is real today. There we go. All right, so now we've got this, and remember, we're trying to figure out what little h is, and conveniently this cancels, and I'm left with a function solely of y. If this does not happen at this stage, you've done something wrong, or the function is not conservative. At this stage, the left-hand side is a function solely of y. The right-hand side better also solely be a function of y. If we're going to compute h, we need to anti-differentiate this. You may or may not know that the antiderivative of 1 over y squared plus 1 is the arctan of y, and then there's an unknown constant c. I immediately then can jump up here and write the full potential function e to the xy plus sine of x plus arctan of y plus c. Now, don't just wipe your brow and say, phew, we're done. We're not done yet. Remember, we're trying to compute this integral. So we're trying to compute it along the curve y equals sine x from 0 to pi over 2. Let's get ourselves a plot of that so we can figure out what the endpoints are. So sine of x, y equals sine of x from 0 to pi over 2 looks something like this, right? That's a 1 there. And there's the starting point and the ending point. The start point is 0, 0, and the end point is pi over 2, 1. What are we going to do now? We're just going to compute the integral c f dot dr is f of pi over 2, 1 minus f of 0, 0. How do you figure that out? You plug those values in up here and do the calculations. I'll leave that to you. It's important to note here, it's the portion of the curve from x equals 0 to x equals pi over 2. That gives us the direction of the curve, and it tells us the order of subtraction. That's really important because otherwise you're going to get some stray minus signs. If you do that subtraction, I did it in advance, I won't bore you with the details, you get e plus sine of 1 plus pi over 4 minus 1, whatever that means. Okay, let's move on here. So in 110, for the following exercises, just determine whether the vector field is conservative and find its potential function. So once again, we're going to apply the test for conservativeness. We've got p here and q here. Let's find p sub y. That's the derivative of this thing with respect to y. 2x minus 2x sine y minus, again, the derivative with respect to y minus cosine x. All right, let's compute qx. Qx is the derivative of this thing with respect to x, negative 2x sine y, looking promising, and then the derivative of that with respect to x minus cosine x. They are equal, so this is conservative. Now we're not asked to do any integration here, but we are asked to find the potential function. So we need to find f so that f, big F, is equal to the gradient of little f. All right, let's do that. So now we're assuming that this piece is f sub x and this piece is f sub y. And again, we'll just start with f of x, integrate, yada, yada, yada. So f sub x is 2x cosine y minus y cosine x. Let's anti-differentiate with respect to x. X squared cosine y minus y sine x plus some constant that depends on y, because we're integrating with respect to x. Another way to think about this is if I differentiated this with respect to x, this piece would go away because it has no x dependence, and we would be right back where we started. Okay, now that we have this f, let's compute f sub y. The derivative of this with respect to y is minus x squared sine y minus sine x plus h prime of y, the derivative of the constant with respect to y, as strange as that sounds. And we know that that has to equal this term up here, minus x squared sine y minus sine x, like so. This one's even cleaner than the previous one. Let me include more space. So for this one, we set them equal. We get almost total cancellation, and we get h prime of y is equal to 0. That's an antiderivative we all can do. We see that h of y is just some undetermined constant, which we can then take back up here and write the potential function. And that's the most general form of the potential function. Let's keep going. Here we're asked to evaluate this integral along any path from 1, 2 to 3, 2. Now, when you see a problem like using that kind of language, any path, this thing better be conservative, otherwise you don't have enough information to do it. If it's conservative, then it's independent of path, and we can handle C being any path, right? That's a clue that this must be conservative. Otherwise, we don't have enough information. Now we know that this is conservative because instead of a capital F here, we literally have the gradient of F sitting here. So that's a conservative vector field. The gradient of F is a conservative vector field by definition. So thankfully, they've already computed F for us, or they've given us little f, so there's not much work to be done here. The fundamental theorem of line integrals, FTLI, says that this is just f of 3, 2 minus f of 1, 2. And remember, the order is determined by from 1, 2 to 3, 2. So this is the start, and this is the end. And remember, we plug in the end, we plug in the start, we subtract. Let me just check my notes here because I've done this one also. This just works out to 14, and I'll leave those details to you. Let's do another one. So here we're given some vector fields and some diagrams of paths, and you're asked to compute the line integral of f over C2. Here's f, okay, here's f, and here is C2, this blue, these sort of turquoise arrows from the origin to 1, 1 and then to 3, 1. Now this segmented path could be really painful because we would have to parameterize in two pieces, do two separate integrals and add them together. Our hope is that this is a conservative vector field. Why is that our hope? Because then I don't care about these two line segments. It's independent of path. I can just start here, end here, take the endpoint, plug it in, starting point, plug it in, and subtract. So let's see if f is conservative. Let's hope that f is conservative. So here's f, p, q. P sub y, the derivative of p with respect to y is 4xy. The derivative of q with respect to x is 4xy. Yay. I love when that happens. It's conservative. F is conservative. What's the next move? Well, now we have to find little f, the potential function. Okay, So now we've got that it's conservative, so we're going to assume that this is f sub x, this is f sub y. F sub x is 2xy squared. We're going to integrate that with respect to x to get x squared, y squared, plus, you got it, some undetermined constant that might depend on y. Now we're going to take the derivative of f with respect to y. We get 2x squared y plus h prime of y, the derivative with respect to y. That, on the other hand, had better equal the other side, 2yx squared plus 2y, like that. We see a little bit of cancellation, and we find that h prime of y has to equal 2y, or that hy is equal to y squared plus some constant c. Now that we've found h, we take it back up here, and we have x squared plus y squared plus c. That's the potential function. We're not done yet. Where does this segment start? Where does it end? And we know that the integral along C2 of f dot dr is little f of 3, 1 minus little f of 0, 0. And I think I've done this one in my notes also, so I'll save you the suspense here, and that works out to 10 if I've done my arithmetic correctly. All right, so it's brilliant, isn't it? Like if you have conservativeness, then the curve doesn't matter, right? And these things become a lot simpler. That curve not mattering, again, I can't emphasize enough how cool that's going to be in the coming days. It's amazing how much you can make out of that quality. All right, I thought it would be important to do a three-dimensional one, so let's do that. Here we have a curve. Now, I want to make a note here, and I've reported this typo to the textbook authors. This little symbol right here, this indicates a closed line integral. It's telling the reader that this integral is along a curve that's a closed path. This is not a closed path. It is just kind of a space curve, and it has a start and an end, and they don't close in on each other. So this is a typo, and it's misleading because it makes the reader think that it's a closed path. And if it were a conservative force field, then we could immediately say that it's 0. So it forces you to kind of look really closely at this path, and that's not good. This symbol is reserved solely for closed paths, and this is not a closed path. So the correct way to note it would be the integral over c f dot dr with no little circle in the middle of the integral sign. Is that clear to everybody? Okay. Bueno, let's keep going here. This is now P, Q, and R, and we've got the three-part test of conservativeness. So the 3D test for conservativeness. And I always just kind of remember that this is secretly fx, fy, fz, and all we're really doing in this test is equating mixed partials. So let's look at the first two. We want fxy to equal fyx, so that means we want py to equal qx, and that's the same test as the 2D version. We also want fxz to equal fzx, so that means pz better equal rx, because those are mixed partials. And then finally, we want fyz to equal fzy, so we're going to need qz to equal ry. So you don't have to memorize these equations. If you just remember that mixed partials are equal, that'll get you there. All right, let's look at py equals qx. Py is 0, qx is 0, check. pz is 3x squared. Rx is 3x squared. Check. And then finally qz is 2z. And ry is also 2z. Check. This is conservative. Now I'm brushing over a little bit here. This is a polynomial vector field. In other words, each of the functions p, q, and r are just polynomials in x, y, and z. These are the nicest possible functions. They're continuous, they're differentiable everywhere. The domain is all real numbers. And so in this particular case, we're fine. The only time you have to worry about getting a true, sort of getting all three of these equations to be true and yet not having a conservative function is when there are discontinuities. But when the function is continuous in the region that you're talking about, if these mixed partials are equal, you're fine. And that's the case here. Great, so this is conservative. That means we have to find, to do the integral, we need to find little f. So find little f so that big F is the gradient of little f. And this is just a little extra work, but the idea is the same. And we're just gonna, again, start with fx. Fx is 3x squared z. I'm going to integrate with respect to x cubed z, and I'm going to add a constant. Now the difference here is this constant is going to depend on y and z. I integrate with respect to x. I might introduce a function that has y and z, no x dependence. What am I going to do next? I'm just going to go and look at fy. Fy is 0 plus the partial of h with respect to y. And fy better equal z squared. Like that. Okay, so then what's h? H is anti-differentiate z squared with respect to y. Y z squared plus, what do you think? Well, you guessed it. This is going to be a constant that possibly depends on z. I don't know what I'm going to call it. Let's call it g of z. So now we've learned a little bit about f. We know it's x cubed z plus yz squared plus g of z. Well, how are we going to figure out the g of z? Well, yeah, you're right. We have a third coordinate that we can work with. So let's take the derivative of f as it now stands with respect to z. Doing so, I get x cubed plus 2yz plus g prime of z. And notice I'm using prime now because there's only one variable left. And that needs to equal the third component, x cubed plus 2yz. X cubed plus 2yz. And lots of cancellation happens. And what I find is that g prime of z is equal to 0, or g of z is equal to a constant. And now I can finish my f, x cubed z plus yz squared plus some undetermined constant. That's the potential function. Again, don't wipe your brow and walk away. You're not done yet. We need to compute this line integral. Well, we know it's conservative, so it's independent of path. That means we can plug in the endpoints and subtract. What are the endpoints of this curve? Well, we need to find r of 4, which we get by plugging in t equals 4 here. That's going to work out to natural log of 4 over natural log of 2, which is just a fancy way of writing 2. And then plugging 4 into the next slot, that's 2 cubed, that's 8. And then finally plugging 4 into the last slot, that's going to be 4. So there's the end. What's the start? It's r of 1. Plugging 1 in to the first coordinate, I get 0 because the natural log of 1 is 0. In the second coordinate is 1. And in the third coordinate, it looks like -1. Yep, and that's the start. Now plug those in, and the line integral C f dot dr is going to be f of r of 4 minus f of r of 1. And I've done that work for you also, I think. Yeah, and that comes out to 159. All right, let's keep going here. 143, last one. So here you're asked to find the circulation and the flux of the field around and across this closed semicircular path. You might not notice it here, but this is a closed path. Let's say you start here at A, you go along the circular arc here, and then across the bottom. It's a two-part path, but together it's a closed path because the starting point and the ending point are the same. This is somewhat of a review. I think mostly this is here to show you what a closed simple path looks like, and to maybe just fool you. If F were a conservative vector field, we would have to do no work. We would immediately say, oh, it's path independent, it's on a closed curve, the integral is 0, and walk away, at least for the circulation. The flux we would still have to work on. But that's not what's going on here at all. This F is not conservative. How do I know it's not conservative? If I take the partial of this with respect to x, I get 0. Actually, it looks like it might be conservative. Hold on for a second. No, we're fine. P, Q, partial P with respect to y is -1, partial of q with respect to x is 1, they're not equal. P, y equals -1, that's not equal to q, x, which is 1, not conservative. So this one, you just have to do the work. Let's talk about circulation first. Circulation is just one of these integrals around C, and you could actually use a little closed symbol if you wanted, f dot dr. But we're going to have to break this up into two pieces. An integral along C1, let's call this C1 and C2. An integral along C1, f dot dr, plus an integral along C2, f dot dr. Okay. Now we're just back to regular old parameterization, and I'm going to kind of shortcut a little bit because these are ordinary line integrals that just require you to parameterize C1 along this arc, which you have here, and then C2 along this straight line segment here. So if you do that work, let me get my notes out here again. That first integral is going to work out to be, I'll give you an intermediate step here, that first integral is going to work out to be 0 to pi of a squared dt plus the second integral minus a to a of 0 dt. That second one, of course, works out to 0, and the first one, of course, works out to pi a squared. So I'll let you practice setting up those integrals. Let me make a little bit more space for myself, and we'll talk about the flux integral. Flux integral is a little bit more complicated because we actually have to find perpendicular vectors to the path. So let's look at R1. The derivative of R1 is minus a sine of t, a cosine of t. And the normal vector along the curve, n, or a normal vector along the curve, can just be what we get by switching the coordinates and changing the sign on one of them. So this is normal to the path, and that's what we need for flux integrals. And that's normal along C1. Let's look at the other path, R2 prime. R2 prime is simply 1, 0. and something that would be normal to that, and would be just swapping those coordinates. You could change the sign on one of them, but it doesn't matter. The 0 relieves you of having to do that. And that also is normal to the path. And then you might remember that the flux integral along 1 is just the integral along C1 of f dot n ds. And that happens to work out to be along C1 f along the path, so f of a cosine t, a sine t, dotted with the normal vector, in this case a cosine t, a sine t, and then dt, like that. And in fact, I can replace C1 with the limits of integration 0 to pi. If you do that calculation, you're going to end up with 0. So I'll let you plug in, figure out f, and complete that calculation. And then flux along 2, integral along C2, f dot, this is n1, f dot n2 ds. That's the integral. We're just going to go from minus a to a. And f along this path, right? Along this path, it's just t0. If I plug that into f, I get 0 here, t here, tj. And then I'm going to dot that with the normal vector, so I'm just going to get a t dt. Integrating that, I also get 0. Putting them together, the whole integral f dot n ds along the whole curve is 0. Is that believable? Sure. If you look at these arrows, they're all tangent to the arc here. So the flux, which is normal to the arc, all perpendicular. And so we would expect that integral to be 0 along that arc. And then similarly here, along this section, the vector field is perpendicular, like that, to the path. And so once again, the flux adds up to be 0. Okay, questions? Well, questions. We're not live, so you can't ask me questions. Suggested exercises. All of the exercises at the end of the section are fair game. I just want to let you know again that exercises 134 and 135 should not be using the closed line integral symbol that you see there. Try a bunch of exercises, sort of try to absorb this notion about conservative vector fields, and when you're ready, go ahead and tackle Chapter 6, Section 3 on web work. All right, thanks.